Hello, hello. Welcome to a great, grand, glorious day of pre-calculus. Today, we're going to be talking about functions and all the weird, crazy things that they are, what they do, and how they be. So go ahead and put away those distractions, pull out those notes, and here we go. So before we can really talk about functions, we have to talk about this other idea called a relation. Now, a relation is a set of ordered pairs, is a the typical kind of entry-level definition for what a relation is. So it would look something like, let's see, we've got an ordered pair 1, 4, 2, 3, 1, 5, and there's my set of ordered pairs. That's a really boring definition for a relation. A relation is pretty much anything that takes an input and has an output. It's kind of more how I remember learning it when I was in school. So technically a blender is a relation because it has inputs and outputs. You put in some fruit and stuff and things and you get out a smoothie. Or if you put in some ice cream and stuff and things, you get a milkshake. Different inputs have different outputs. So you're not really necessarily locked in with one input and one output when you're talking about a relation. Anything with inputs and outputs can be relations. Students going into a high school, and all sorts of other various fun things. But this is the kind of more boring ones that we're going to be talking about in school. So this is a set, because we got those curly brackets, right? Set notation, all that fun stuff. And we have some ordered pairs. This is kind of a boring way to represent this particular relation. There's other ways that we can do this. We can take 1 and 4, and let's see, my outputs are 3, 4, or 5. We put them in a circle. So here's my inputs. My inputs. Here are my outputs. And let's see, one ordered pair went from 1 to 4. One ordered pair, oops, that's supposed to be a 2, not a 4, silly. Went from 2 to 3, and another ordered pair went from 1 to 5. So that's another way of representing this particular relation. You might see them listed like this, because anytime we have ordered pairs, we can also write them down on a table. We can also graph them, right? So here's 1, 2, 1, 2, 3, 4, 5. So 1, 4, 2, 3, and 1, 5. Not drawn to scale. So here's 1, here's 2, here's 5. So these are all different ways that we can represent a relation. Table, this guy over here, this is called a mapping. A map. We have our ordered pairs, and we also have our graph off to the side there. So that's how we can represent relations. Now, whenever we start talking about relations, we want to talk about another really key idea, and those two ideas are domain. And the other one we want to talk about is range. So when I'm talking about domain, the domain is the set of inputs for a relation. So all of my input numbers. So a mapping is actually the easiest way to find your domain. Let's see if the highlighter will work today. No, it won't. All right, beautiful. Here, right here, this is the set of all of my inputs. If I'm looking at some ordered pairs, we would go this guy, and this guy. If I'm looking at a table, it's my first column. And if I'm looking at a graph, it's like, okay, so this dot is part of here, this dot's part of here, this dot is also part of here. So that's my domain. And we write it as a set. So the domain for this particular relation we've been playing with so far is 1, 2. Notice it's not an ordered pair. I don't have parentheses or anything along those lines. It's just the set and a list of what's in there. The range is the set of outputs. And so mapping, again, really nice. Tables, nice and easy. Graphs, a little more irritating. So we got 3, 4, and 5. And then the ordered pairs, it would be the second part of the ordered pair. That would be considered the output. And so my range is 3, 4, and 5. So I've got my domain and I've got my range, and those are my things that I've got going on here. All right, so a function, because that's what we really want to talk about here, is we want to talk about functions. So a function is a special type of relation. It is a relation where that assigns each element of the domain. So everybody over here in this side of the mapping, in my domain, each of these guys gets paired with exactly, precisely one single element in the range. So Saying that again, a function is a relation that assigns each element in the domain to a single solo element in the range. So this relation that we've been playing with up above it's a function. And no, it's not. One clue is that my range is bigger than my domain because I have more outputs than I have inputs. And we can see that right here with number 1, he has 2 things that he's reaching out towards. So when you're looking at a mapping or ordered pairs, I like to think of functions or they're like one-armed bandits. They only have one arm and they can only grab one output as they're going along. So this guy goes to this guy, we'll make him a smiley face, goes over here to star. You can even have 2 things going to the same one. Like those guys can both point to the same thing. You can have the same output, that's perfectly fine, but the input can only have one output. He can't have two different outputs. That's not allowed. Blender is actually a really good example of a function because if I put something into a blender, I'm not going to get 2 different things out. If I put the ice cream and the milk in there, I'm going to get a milkshake. Fruit and some ice, I'm going to get a smoothie. A phone, should not put phone into blender. Little brother's fingers probably also should not go into blender. So yeah, we've got different things that we can and can't. So just because it's a number doesn't mean it's included in my function. There's lots of numbers that aren't part of that. All right, so let's look at determining whether the domain, finding the domain and range of various relations, and then also determining whether or not it is a function. And you guys have it already on your paper, which is great, grand, and glorious. I, however, do not. So let's start looking at some examples. So the first example you guys had was a set of ordered pairs. We've got -1, -1. We've got 7, -4. We've got 3, 0. And last but not least, we have -5, -1. All right, so there's my thing. So now looking first I'm supposed to find domain, then I'm supposed to find the range, and then I'm supposed to determine whether or not this thing is a function. So domain is always just the inputs, and the inputs are the first guys. So my domain, we usually abbreviate with D, is equal to the set -1, 7, 3, -5. Now I can hear you asking, Norton, does it matter if I put them in order from smallest to biggest? It's considered polite to do so. We usually do that, but you're not wrong for doing this way. You're just like speaking with a weird accent. So if I was to put those guys in the appropriate order, we would go -5, -1, 3, and 7. And then we would have things in their appropriate relationships to each other. Next up, we have range. And so the range is the set of outputs. So those are the quote-unquote Y values, right? The second part of my ordered pair. So I've got, again, -7, -4, 0, -1 again. Okay, we've got doubles. We don't list the doubles because we already have -1 in the list. I don't need to add them twice. So cleaning this up a little bit, we've got -4, and then we've got -1, and then we have 0. And that's my range. So the next question is this a function? Does each input only get mapped or connected to one output? Another way of looking at it, when I've got a list of ordered pairs, is each number in the domain listed only once. So I only have one -1 for my domain, I have 1, 7 for my domain, I have 1, 3 for my domain, and I have 1, -5 for my domain. So it's okay. But Norton, the -1 and the -5 are both mapping to the -1. Yeah, that's fine. It's okay. No big deal. Okay, moving on. We've got our next one. We've got the nice little swoopy of our X values, and then our swoopy of our Y values. I love it when it's set up like this because this whole thing is just my domain and I can just write the numbers down. So domain in this case is -2, -1, 0, 1, and 2. And then my range, again, is going to be just this guy here, whatever numbers happen to be in there, 0, 1, and 4. So for this middle example, is this a function? So each one of my little doohickeys, I'm going to go and I'm going to look at all of the arrows or all of the numbers that are in there in the domain in my first one, my X one, and I'm going to make sure that they're only getting mapped over to one other thing. So like if I had like say -2 in here and he was getting mapped over to 0 and then he was also getting mapped over to 1, something like this, now he's a 2-armed bandit, and that's not okay. So, but does that happen in this particular example? No, we are good to go. We don't have any of this 2-armed nonsense going on. 2 is just getting mapped over to 0. So that's okay. Taking a look at the next function, we do have some 2-arm shenanigans going on because the -9 is getting mapped to the -2 and to the +5. So that guy is not a function. That doesn't mean we get out of not having to name the domain and range. Every relation has a domain. Every relation has a range. They have some sort of input. They have some sort of output. So you do need to write those down. All right. So moving on to the graphing ones, because those are the fun ones. And I really should have put those pictures in here. Bad, Norton. Okay. It's okay. It's okay. It's okay. All right. So here is my graph, approximately. Bloop. So when I'm looking at a graph, my domain is typically, as we did kind of up above, domain is typically assigned X because it's the independent variable, it's my input, it's all of that fun stuff. And I'm trying to figure out which X values is getting used on this particular graph. Now this guy's a circle, right? We've played with circles before. So my smallest X value, usually what we do is we start over here with our little dude, and he walks this way. And I'm going to go looking for the smallest X value that my thing is using. So here we go. -3. He's part of the graph of this particular relation. All right, so -3, and we keep going. I've got stuff up here, stuff down here. Okay, we're good. Good. Still using values until right about there. And then all of a sudden, we're not using the values anymore. So we're no longer within the domain of this particular relation. So where did it stop and where did it start? Where did it stop? We started, my domain is going to start at -3 and it stops at 3. Important question. Does it include those values? Yes, it does. So we get to put square brackets on this thing if we were writing things in interval notation. Don't forget, we also have our wonderful set notation, which we would say -3 is less than or equal to X, which is less than or equal to 3. Squiggle bracket. All right, so there's that. Then we're going to put a little dude over here. Does he go on the top or the bottom? We always start with the lower numbers and work our way up. So we're actually going to put our little dude down here. And he's going to go that way. So here's part of my function. And then nothing out here. Okay, so my range looks like it's going to be the same as my domain. And then for range, now your graph specifically says that this is the X and this is the Y. So instead of saying X such that, we're actually going to say Y such that -3 is less than or equal to Y, which is less than or equal to 3, because we're talking about range. And those are Y values, not X values. The last most important question, is this a function? Function? Yes or no? So when we're talking about things with graphs, we actually have a sneaky way that we can do this. It's called the vertical line test. So if I take a ruler and I slop it down 90 degrees, boop, can I make a line that touches the graph, the function of the graph, or the picture part of the graph more than one time? In this case, yes I can. It's a circle. There are definitely 2 outputs for different inputs, for most of my inputs actually. So if I look at 0 here, right? There's this output and there's this output for the X value or the input of 0. So these guys are not a function. No, not function. But it is a really fun little thing. It is a relation. It's just not a function, which is perfectly fine. All right, so next up, we've got this guy, right? And he starts here, 1, 2, 3, and then he goes up to 2, and then we come down to 2, and we go shoopy. This guy's called a piecewise function. All right. Domain starts right here. So we got my dude. Dot. He doesn't hit the function until right here. And then, yes, we still have the function, still have the function, still have the function, still have the function. So there's like function stuff up here that we're mapping to. And we're still grabbing hold of. Uh-oh. We got an arrow going off this way. So that function will just keep heading off that direction. So my domain starts at -3 and keeps going off to infinity. Yay! To infinity and beyond. So, oh wait, I forgot to write the D. So domain. And then R for range. And we're going to start my little dude down here. And he's going to walk this way. And then right here, there's technically 2 values. Yes? Story time. Oh, well, I better go do story. Give me just a second to finish this example and I'll be right there. So he's going along, boop. And right there, it kind of feels like the domain or the range would end, right? Because it turns around and goes back down. Be sneaky. So we've got these guys, but then don't forget about these guys over here. I still have y values that this function is feeding me, and it's going to keep on going up and up and up and up and up. So my range actually starts here and keeps on going. So my range starts at 0 because I do actually touch 0 in 2 different places, and it goes off to infinity and beyond. And of course, the most vital question, is this a function? So does it pass the vertical line test? Can I draw a vertical line on here that touches that blue line more than once? The answer is no. No, I can't. So yes, this is a function. But Miss Norton, how do you know? Because maybe this thing keeps going and then loops back around on itself. It is implied with an arrow that it's going to keep going that direction forever. That's what the arrow means. If there was any more interesting things going on, we would have to show that on the graph. So yes, this is a particular function. Take a look at the next example, see if you can figure out what's going on there, and I'll be back. And we're back. Okay, so there's all of that great grand glory stuff. All right, go ahead and turn the page. I just realized I only have 14 minutes left. I got a lot of talking to do and not much time to do it. All right. We have on that page f of x equals 2x plus 4. So how I said that out loud, that's actually how you English this. This right here, this right here is the name of the function. You can use anything to name a function. We typically use the letters F, G, H for naming functions, but you can use any other letter. We use lowercase functions in pre-calculus. Uppercase letters mean something specific in calculus class, so we try to stick with the lowercase letters here. You can be silly and call it smiley face of x or anything else like that, but f of x works for this. All right, then this is the input variable. So this is the thing that we are putting into our function, and it's doing stuff and things and whatnots. And so that's the thing that as we're going along over here, we know what we're going to be changing. Because sometimes you'll see something like 2x plus 4y. Okay, so the x is the thing that's changing. The y would just stick there along and be along for the right. We're not going to do that right now. And then this right here is known as the function rule. This is the thing that is happening to the inputs of the function. So you can kind of think of functions as a machine. This machine's name is f, and the inputs that are getting chucked in here are x. The thing that's going to happen to x is 2x plus 4, and then what's going to come out is f of x. So if we're talking about those ordered pairs, because relations are sets of ordered pairs, functions are relations, the ordered pair for this is x comma f of x. And that would be my ordered pair. And so then the different things that I can snag for my domain and put into here will give me the different outputs, and so on and so forth. All right, so there's that gloriousness. Was there anything else I wanted to talk about? Nope, I've told you how to English this. We've done the function, we talked about the ordered pair. Beautiful, beautiful, beautiful. All right, on to examples. So we've got a lot of examples on here that we are gonna go through. I'm gonna try and focus on just the highlights because I am running low on time. If I've got more time, I'll come back and do some of the others. So a classic example would be something like f of 3, and we're going to use that function rule up there. So kind of writing it closer so I can see it, 2x, oh, we got a new function, 2x squared minus 3x. There's my new thing. So what we're going to do is instead of x, everywhere I see an x on my function rule, 2x squared plus minus 3x, I'm going to replace the x with the 3. That's what function notation is telling me to do. So we're going to do 2, and we're going to replace it inside parentheses. So 3 squared minus 3 parentheses, 3 close parentheses. Now, order of operations become vitally important here. It is very, very important that you follow order of operations correctly and precisely as you are evaluating functions. It's really easy to get up with these really, really tangled webs that look really, really complicated. Just fall back, trust your order of operations, parentheses, exponents, do the multiplication division from left to right, do addition subtraction from left to right. So our first order of operation is exponents, and that's going to give me 2, this guy's still in parentheses, minus 3 parentheses 3, and that's going to give me 18 minus 9, and then that's going to give me 9 as a final answer. So there we have it. That is the thing. And then let's see, we're going to do 3 f of x. I like talking about this one because this means we're going to be putting basically f of x because it's on the outside. So whenever we're replacing things on the inside, we always use parentheses. Whenever we're doing something to the outside nonsense, we usually put the function because wrong color. This right here, this f of x, we're going to rewrite that 2x squared minus 3x. And we're going to put that whole thing in its own set of parentheses. Because we need to remember that when I'm taking this function, I'm multiplying it by 3, so I need to multiply everything that's in there. So that's going to give me 6x squared minus 9x, and that's 3 times f of x. Okay, so not too bad, not too bad. Next up, let's compare f of negative x with negative f of x, because these are two different things. So f of negative x means that everywhere I see an x, I'm going to replace it with negative x, and it's going to be squared, like so. So this turns into 2, that's x squared, Maya plus 3x, 2x squared plus 3x. Yeah, I did 2 steps at the same time. Whereas this one is negative 2x squared minus 3x. So everybody's sign's going to change like so. So there we have our two different things. Okay, so f of negative x versus the opposite of f of x, or f of negative x. And I really want to look at this guy right here. This thing is important. It's going to be part of something that's going to haunt your nightmares for math class all the way into calculus. It's going to come back and haunt you again and again and again, this f of x plus h. So we got to talk about it. So we're going to have 2, and then x plus h. We got to remember to do that, right? So x plus h, it's going to be x squared plus xh plus xh plus h squared minus 3x minus 3h. So 2x squared plus 4xh plus 2h squared. Those two combined into that, minus 3x minus 3h. And that's it. That's as simplified as this thing gets. Do not try to factor the shenanigans. We just expanded it out, and we did that for a reason, for stuff and things down the road. We'll talk about it later on in this module. So that's how that guy goes. Looking at the graph, man, gosh darn it. Once again, I wish I had this picture in my book, but that's okay. 1, 2, 3. Starts here, and we go up to here, and then we go over to here, and then down to here, and then putting our tick marks, doot. Okay, so I'm looking, and we're going to call this function, we're going to call it g, boop, and I'm looking for g of 1, so I'm going to go find 1 on the x-axis, it should get mapped to only 1 point, and it does. The y value for that point is 2. Because remember, this is an ordered pair, 1, 2. This is the input from the domain. This is the output from the range. So my answer for g of 1 is equal to 2. We can also do g of 3. So 3 is over here. And that output is 0. And last but not least, we're looking for g of negative 2. Oops. And that would be, negative 2 is here. We got to figure out what's this point. Well, okay, looking at that picture and kind of looking at how the slope of that line goes, I'm pretty sure this value is going to be 1, because this up here is at negative, is up 2, and this one down here is at 0, so the one in the middle must be at 1. All right, moving right along. 7 minutes to talk about the most important thing. Oh boy. Okay, there's 3 rules when it comes to finding domain algebraically. You have already encountered 2 of these rules multiple times within your mathematical careers. We just haven't ever spelled it out for you, black and white, or in this case, black and red. All right, so the first rule when it comes to domain, finding domain algebraically, do not divide by 0. That's that's important. We never ever actually break that rule. This is not one of those weird things where you get into more advanced math classes and then you learn that, well, actually, no, that one we never break. Do not put a negative number inside a square root. So we can't take the square root of a negative number. Now, so like that doesn't mean like, we did on the last test where we had like 3 x plus 2 square root x equals -1. I can do that. That's fine. It's when I get done simplifying and I would and I somehow end up with the square root of -11. That's not okay. So that's kind of what we're talking about. We can put that in here. That's okay. This is not. Okay. And step 3 is the one that you might not know of as much. We only put positive numbers inside of logarithmic functions. So we'll talk a little bit more about that down the road. You should be starting to get familiar with logs. They're going to haunt you quite a bit. So when I have a denominator, so let's say I've got some fraction and blah, 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 and here's my denominator. I can't let that equal 0. So I set up an equation like that, and I solve that equation. When I have a square root, and I've got this stuff inside, I have to say that that stuff inside has to be greater than or equal to 0 because I can't allow it to be a negative number. And when I have a log, sometimes there's a little number here, and I'm taking log of something, that has to be positive. It cannot be 0. Can't be 0. So I'm just going to say greater than 0, not greater than or equal to 0. So those are my 3 setups for my 3 different things as I'm going along. So the first one we've got there, f of x is equal to -x minus 5. So what we do whenever we encounter a function and we're trying to find the domain, we go and we check our 3 rules. 1, can I divide by 0? Well, I don't have a fraction, right? There's no fraction nonsense, so no, can't break that rule. Do not put a negative inside of a square root. There's no square root. Only positive numbers inside of log. There's no log. So if I can't break any of the rules because it doesn't meet any of the possible conditions, my domain is going to be all real numbers. That's like goofy R, 2 backbones, and a swoopy. So don't forget that. Next up, we've got 2x plus 2 divided by 4x minus 12. So we have a new function. Usually we would give the new function a new name. This one, I can break rule number 1. Is a possible break here. So I'm going to take this denominator, 4x minus 12. I'm going to say that can't equal 0, because then that breaks math. So that would give me 4x can't equal 12. Therefore, x can't equal 3. We treat it just like we would any old ordinary equation. We just go along and just treat the equal sign like a not equal sign. Or treat the not equal sign like an equal sign. That. I'll let you guys play with the next one down, the one that has the x squared. Come on. Wow. X squared plus 2x minus 8. You would say that can't equal 0. Some factoring is going to come back and haunt you on that one. Let's see. We've got the square root. F of x equals the square root of 7x minus 49. So I'm going to take the stuff inside the square root. So this is going to break rule number 2. This was rule number 1. 49, and that has to stay greater than or equal to 0. Hey, it's like that stuff we did about inequalities coming back to haunt you. Yeah, there was a reason for that. So x has to be greater than or equal to 7. And again, you can write this in interval notation, so greater than or equal to 7, so that would be a square bracket, 7 comma infinity, or the interval notation like so, same thing. All right, next up, we have f of x is equal to negative log base 3 of x plus 3. It's a log. I don't care about any of the crap outside of the log unless they can also break one of the rules, but it can't because it's just a negative sign, so who really cares about the negative sign? We're going to take this x plus 3 nonsense, and that has to be strictly greater than 0. We can't allow the log to be equal to 0. So we're just going to be greater than 0. So that means that I moved that -3. So I'm going to go from parenthesis -3 to infinity, and that's my domain for this guy. All right, domain x such that, there, boom. All right, last but not least, we have the fun ones. Ooh, I've got 1 whole minute for the fun one. All right, x minus 5 over the square root of 5x plus 25. That was rule 2. This was rule 3. This is rule 1 because fraction, and 2 because square root. So first off, the 5x plus 25 can't equal 0. Second of all, so that's what rule 1 says. Rule 2 says that 5x plus 25 has to be greater than or equal to 0. Now hang on, those 2 rules are kind of contradicting each other. This guy is saying can't be equal to, so this part right here that part right there, we have to take that off. So we're going to be basically treating this like it's a log, greater than 0. We have to say it that way because we can't let the denominator equal 0. We can't divide by 0, and we can't put the negative number inside there. So we're only looking at this one particular spot on the number line. X is greater than 5. Bada bing, bada boom. All right, there's 2 extra little challenging questions on there. And do you know how to solve inequalities involving quadratics? Ooh. All right, but I'll go over that. But if you're good to go, you may leave at this point. I'll go over those extra ones just because they're fun. But yeah, for the rest of you guys, happy mathing. All right, now the fun one. Because why not do the fun one? Because we can and it's there. So f of x is equal to the square root of x squared minus x minus 12. So again, we're breaking rule number 2 with this guy. I can't allow negative things to fall into square rooties. So we're going to take x squared minus x minus 12, and we're saying that has to be greater than or equal to 0. All right, so that's the thing. Factoring is always a good first move when playing with quadratics. If you can factor, we always factor. Okay, so now we want x minus 4 times x plus 3 to be greater than or equal to 0. The equal to 0 part is easy, right? X minus 4 equal to 0, and that's going to turn into x equals 4. X plus 3 is equal to 0. X equals negative 3. But what about the greater than part? Well, this is set up as a multiplication thing, right? So what we do is we draw out a little number line. We got negative 3 over here. We've got 4 over here. We're going to make this a little bit bigger. And basically what's happened is we're going to try and like graph this thing on the number line, and we're going to utilize something called test points. So we know that the zeros are in. And when we get to a 0, that's when we switch from negative to positive or positive to negative. Sometimes we just come down and hit it, and we stay on whichever side of the thing we're on, either negative or positive. And we'll get into that in a future chapter. But right now, we're just talking about the quadratics. And so what we would do with this is we would take, okay, so I've got the factor x minus 4. I've got the factor x plus 3. And then down here, we're going to multiply those two things together and figure out whether we've got a positive or negative number. So let's say we've got negative 7. These are the only 2 places where things touch 0. So these are the only 2 places where things could possibly change from a positive to a negative number. So if I put negative 7 in here, I don't really care what negative 7 minus 4 is. I'm really focused on whether or not it's a positive or a negative number. So negative 7 minus 4 would give me a negative number. Negative 7 plus 3 is also a negative number. And what happens when I multiply a negative number times a negative number? I get a positive. So this stretch right here is greater than 0. When I plug various numbers in here, and whether it's negative 500,000 gazillion, it's still going to be a positive number because it can't come anywhere close to the 0. It's not going to cross over because these are the only 2 places where this function is going to cross 0. All right, so that's that one. So let's pick another test point that's in between negative 3 and 4. 0. 0 is my favorite number. If I can grab 0 for these guys, I always do. So 0 minus 4 is a negative number. 0 plus 3 is a positive number. A negative times a positive is going to turn into a negative number. So this is a nope. Don't touch this. Not this area. All right, picking a number over here. For some reason, we're on a 7s kick. 7 minus 4 is positive. 7 plus 3 is positive. That's going to give me a positive number. So these numbers are also in, and they're good to go. So then putting this in my set interval notation, we're going to go like this. And then we got a gap. And then we start back up at 4. And we go on to there. And that's how that works. The next challenge question is really, really similar. We just threw the square root into the denominator. So instead of having closed circles, we'll end up having open circles at whatever those factor points are. And then we'll have to do our test point, our test point, our test point, and we'll figure out where things are positive. So that'd be that. Anyway, thank you so much for sticking around for the challenge part, because this is the fun bit. And have a great rest of your evening. See you in class. Happy mathing!